Yeah. Good morning, sir.
Yeah.
Good morning, ma'am. Good morning, Sanjay. Good morning, Professor Krishnan. Good morning. Bharat Ratna, Professor C.N.R. Rao, Dr. Mrs. Indumati Rao, Professor G.U. Kulkarni, the President of JNCASR, Professor V. Krishnan, members of the Governing Council of the C.N.R. Rao Education Foundation, Mr. Sanjay Rao, Award Selection Committee members, distinguished invitees, colleagues of JNCASR, teachers and students from various schools. Actually, we have students and teachers participating from more than 15 schools in mostly online platform, both on WebEx and YouTube. It is my great pleasure to extend a warm welcome to you all for this award ceremony on behalf of the Center and C.N.R. Rao Education Foundation to honor the outstanding science teachers for their dedicated service in educating a large number of students in science. The C.N.R. Rao Education Foundation, a registered charitable trust instituted in 2005, was generously and graciously funded through Professor C.N.R. Rao and his family from their personal funds to promote good quality science education at all levels, both nationally and internationally. The foundation, in association with the C.N.R. Rao Hall of Science and Education Technology Unit of the center, conducts various programs for school children and teachers throughout the year. Student Mentoring Program, now popularly known as SMP program at JNCASR. Flagship outreach programs in Gangoli Hut, Uttarakhand. School Chandan, Lakshmishwar, North Karnataka. We have Mr. Ishwar and his family with us. Sagar Science Farm, Shumaga, are to name a few. Professor C.N.R. Rao Education Foundation has instituted awards for outstanding science teachers in the country. The institution of this award is to honor the noblest profession, teaching and education. The award carries a certificate, citation, and token amount of award money. The foundation has entrusted JNCASR to select outstanding science teachers for the prize annually. On behalf of the center, it is a pleasure to thank C.N.R. Rao Education Foundation and Professor C.N.R. Rao and his family for reposing the selection of the outstanding science teachers to our center. We at the center are justifiably proud and honored to have a distinguished scientist and a revered teacher, Bharat Ratna Professor C.N.R. Rao and Madam Rao for guiding us in all our endeavors. The earlier recipients of the prestigious Outstanding Teacher Awards. Before that, I also would like to thank Professor K.N. Ganesh, Director, ISR Tirupati, joining us. The earlier recipients of the prestigious Outstanding Science Teachers Awards are shown on the screen. Can I have a list, please? Yeah. So these are the list of outstanding science teachers who have received in the previous year. Just for your information, the award is for 2018 are B.S. Girish from Government High School, Vadagere, Tumkur District, Karnataka. Ajay Kumar Bari, Government Senior School, Secondary School, Kartarpur, Jalandhar, Punjab. In fact, I would like to reiterate here that science teachers from all over India, from north to south, from east to west, have received this prestigious award in the previous years. For the year 2019, the center had invited nominations through extensive advertisement in newspapers in the country. We received nomination from all over India. A committee was constituted by the center consisting of eminent educationists, scientists, and teachers, with Professor V. Krishnan as the chair of the committee, Dr. Mrs. Indumati Rao, Professor Y.S. Ramaswamy, Dr. Gururaj Karjagi, Mr. P.G. Dwarakanath, Dr. S.G. Srikanteshwara Swamy, Mr. A.N. Jayachandra, and Mr. Jaydeep were the members of the committee. I am happy to say that the following outstanding teachers have been selected for the award instituted by C.N.R. Rao Education Foundation for the year 2019. The awardees are Shri Ramachandra Bhat, BG from Government High School, Byataranapura, Mysore Road, Bengaluru, Karnataka. The other awardee is Shri Annapu Punnayya from Municipal Corporation High School, Balaga, Srikakulam District, Andhra Pradesh. On behalf of the center, we welcome you, we warmly welcome you and congratulations to you, both of you. The award ceremony was delayed due to COVID-19 pandemic. In fact, the awardees have expressed their interest to attend the function in person in JNCASR so that they have the opportunity to meet with Bharat Ratna Professor C.N.R. Rao. However, no further delay is possible. So for and keeping in mind that it's already delayed quite long, so we that center and the foundation decided to have this function in hybrid mode. Our president, Professor G.U. Kulkarni, has kindly agreed to present the awards today. Now I request, sir, may I request you to come on dais. Now I also request Shri Ramachandra Bhat to come on the dais. Now I request Mr. Jayachandra to read the citation.
Good morning to everyone. It's my great pleasure to welcome the past presidents of JNCASR, Professor V. Krishnan and Professor V. Nagaraja, and also the youngest member of the C.N.R. of Education Foundation, Advi, whom we are seeing, on the screen. This is the text of the citation from the C.N.R. of Education Foundation to Ramachandra Bhat. Sri Ramachandra Bhat BG is a science teacher at Government High School, Byataranapura, Mysore Road, Bengaluru for more than 2 decades. He was involved in modernizing school infrastructure, guiding students to work on various scientific projects and won various prizes at state and national level. Sri Ramachandra Bhat has developed several innovative teaching strategies through low-cost science kits and videos to help high school teachers and students. He has organized student visits to many research institutions and fairs to create interest in science. Mr. Bhat has played a vital role in the Dashadivige program telecasted on the Chandana channel of the Doordarshan, aimed at popularizing science across the state and country, mainly in the rural areas. Sri Ramachandra Bhat is the recipient of several awards. Notable among them are Institute of Scholars, INSC National Level Best Science Teacher Award 2020, Zero Investment Innovation Award from Aurobindo Foundation, Delhi in the year 2019, District Level Best Teacher Award 2017, Pandit Deen Dayal Upadhyay Memorial Award in the year 2012, and state winner of the Microsoft Innovative Teachers Leadership Award in the year 2012. The C.N.R. of Education Foundation takes great pleasure in honoring Sri Ramachandra Bhat for his dedicated work for the cause of science education. Thank you.
You can stand up, sir. You can stand. Yeah, that is good. Jayachandra sir, little tilted, sir. Yeah. Yeah, it's like. Yeah. Oh. I'll hold it. Yeah. Thank you, sir. Our next awardee is Shri Annapu Punnayya from Municipal Corporation High School, Balaga, Srikakulam District, Andhra Pradesh. So Shri Annapu Punnayya is joining us online. So now I request Mr. Jayachandra to read the citation.
Sri Annapu Punnayya is a science teacher at the Municipal Corporation High School, Balaga, Srikakulam District, Andhra Pradesh for more than 2 decades. He has motivated and guided students to work on various projects, successfully exhibited them and won various prizes and the state and national levels. Sri Annapu Punnayya and his students completed many projects and have been awarded prizes at the district level. He has organized many awareness programs, science exhibitions, conducted training sessions in science for students, also rallies on environmental hazards. Sri Annapu Punnayya has been recipient of the Best Teacher Award from the Chief Minister and Education Minister in Andhra Pradesh in the year 2019, World Ocean Science Congress Award in the year 2019 again, Best Science Communicator Award by the Government of Andhra Pradesh, Best Teacher Award at district level from the DEO and the District Collector in the year 2006. The C.N.R. of Education Foundation takes great pleasure in honoring Sri Annapu Punnayya for his dedicated work for the cause of education, particularly in science. Thank you.
Thank you very much.
Mr. Annapu Punnayya, this is the award for you. Are you able to see this?
Thank you.
Please unmute and.
Please unmute. Are you able to see?
Is there?
Turn it around. Turn the camera around.
Yes, yes.
Yeah. Now it's perfect. Perfect.
Yes, sir. Thank you.
Thank you. Thank you very much, sir. Just
Yes,
for your
sir.
kind information, the award, just now we had the felicitation by the president, which include a shawl, a plaque, and also the citation. In addition to that, the awardees have been presented with the books authored by Bharat Professor C.N.R. Rao and Dr. Mrs. Indumati Rao. And the cash money has been already sent to the awardees. So now I request the awardees to give their response, starting with Shri Ramachandra Bhat.
ಎಲ್ರಿಗೂ ನಮಸ್ಕಾರ. ನಾನು Ramachandra Bhat. So this is a great honor to receive such a prestigious national award. So ತುಂಬಾ ಖುಷಿ ಆಗುತ್ತೆ. ಸೊ ಜೊತೆಗೆ ಸಾಕಷ್ಟು ರೆಸ್ಪಾನ್ಸಿಬಿಲಿಟಿಯನ್ನು ಕೂಡ ಇದು ತಂದುಕೊಟ್ಟಿದೆ. ಇನ್ನಷ್ಟು ಹೆಚ್ಚಿನ ಉತ್ಸಾಹದಿಂದ ಕೆಲಸ ಮಾಡೋದಕ್ಕೆ ಇದು ಪ್ರೋತ್ಸಾಹವನ್ನ ಪ್ರೇರೇಪಣೆಯನ್ನ ನೀಡ್ತಾ ಇದೆ. ಸೊ ಪ್ರೊಫೆಸರ್ C.N.R. ರಾವ್ ಅವರನ್ನ ಭೇಟಿ ಮಾಡಬೇಕು ಅನ್ನೋದೇ ಬಹಳಷ್ಟು ನಮ್ಮಂತ ಶಿಕ್ಷಕರ, ವಿಜ್ಞಾನ ಶಿಕ್ಷಕರ ಕನಸಾಗಿರುತ್ತೆ. ಸೊ ಅವರನ್ನ ಇಂತಹ ಒಂದು ಪ್ರತಿಷ್ಠಿತ ಅವಾರ್ಡ್ ಅನ್ನ ಸ್ವೀಕರಿಸುವ ದಿನ ಭೇಟಿ ಮಾಡಿದ್ದು ಅದ್ಭುತವಾದಂತಹ ಒಂದು ರೋಮಾಂಚಕಾರಿ ನಮ್ಮ ಬದುಕಿನಲ್ಲಿ ಅದ್ಭುತ ಅನಿರ್ವಚನೀಯ ದಿನ ಅಂದ್ರೆ ತಪ್ಪಾಗಲಾರದು. ಸೊ ಇಂತಹ ಒಂದು ಅವಕಾಶವನ್ನ ಕೊಟ್ಟದ್ದಕ್ಕಾಗಿ CNR ಫೌಂಡೇಶನ್ ಜೊತೆಗೆ JNCASR ಎರಡು ಸಂಸ್ಥೆಗಳಿಗೆ ಹಾಗೆ ಈ ಅವಾರ್ಡ್ಗೆ ಸೆಲೆಕ್ಟ್ ಮಾಡಿರುವಂತಹ ಎಲ್ಲ ಜೂರಿ ಮೆಂಬರ್ಸಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ಹೇಳ್ತೇನೆ. ಹಾಗೇನೆ ಸಾಕಷ್ಟು ಜನ ಆನ್ಲೈನ್ ಮೂಲಕ ವಿದ್ಯಾರ್ಥಿಗಳು, ಶಿಕ್ಷಕರು, ಶಿಕ್ಷಣ ತಜ್ಞರು ಈ ಆನ್ಲೈನ್ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಭಾಗಿಯಾಗಿದ್ದೀರಾ. ನಿಮ್ಮೆಲ್ಲರಿಗೂ ಕೂಡ ಹೃತ್ಪೂರ್ವಕವಾದಂತಹ ಧನ್ಯವಾದಗಳನ್ನ, ಅಭಿನಂದನೆಗಳನ್ನ ಸಲ್ಲಿಸ್ತಾ ಇದ್ದೀನಿ. ಸೊ ಒಂದು ರಿಕ್ವೆಸ್ಟ್ ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ, ಇಂದಿನ ದಿನಗಳಲ್ಲಿ ವಿಜ್ಞಾನ ಬಹಳ ಕಷ್ಟ ಅನ್ನುವಂತಹ ಒಂದು ಹಂತದಲ್ಲಿ ಇದ್ದೇವೆ, ಒಂದು ಸಂಕ್ರಮಣ ಕಾಲದಲ್ಲಿ ಇದ್ದೇವೆ. ಸೊ ಇಂತಹ ಸಂದರ್ಭದಲ್ಲಿ ನಾವು NEP ಬರ್ತಾ ಇದೆ. ಈ NEP ಸಂದರ್ಭದಲ್ಲಿ ವಿಜ್ಞಾನದಲ್ಲಿ ಸಾಕಷ್ಟು ಕ್ರಾಂತಿಕಾರಕ ಬದಲಾವಣೆಗಳು ಆಗ್ತಾ ಇವೆ. ಆ ಸಂದರ್ಭದಲ್ಲಿ ವಿಜ್ಞಾನಿಗಳು ಮತ್ತು ಶಿಕ್ಷಕರು ಹತ್ರ ತಂದು ಅವರ ಮೂಲಕ ವಿದ್ಯಾರ್ಥಿಗಳಲ್ಲಿ ಇನ್ನಷ್ಟು ಆಸಕ್ತಿಯನ್ನ ಬೆಳೆಸೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗುತ್ತೆ. ಸೊ ಪ್ರತಿಷ್ಠಿತ ಸಂಸ್ಥೆಗಳು ನಮ್ಮಂತಹ ಶಿಕ್ಷಕರಿಗೆ ಸಾಕಷ್ಟು ಮೆಂಟರಿಂಗ್ ಮಾಡೋದರ ಮೂಲಕ ಯಾವ ರೀತಿಯಾಗಿ ವಿಜ್ಞಾನವನ್ನ ಇನ್ನೂ ಸರಳವಾಗಿ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಲುಪಿಸಬಹುದು ಅನ್ನೋದನ್ನ ಚರ್ಚೆ ಮಾಡ್ಬೋದು. ಸೊ ಇದರಿಂದ ವಿಜ್ಞಾನ ಬೆಳೆಯುತ್ತೆ, ವಿಜ್ಞಾನ ಶಿಕ್ಷಕರು ಕೂಡ ಬೆಳೀತಾರೆ. ಸಾಕಷ್ಟು ಸಂದರ್ಭದಲ್ಲಿ ನನಗೆ ಗೊತ್ತಿರಲಿಲ್ಲ, ಇಲ್ಲಿ ಪ್ರತಿ ತಿಂಗಳು ಕೂಡ ಶಿಕ್ಷಕರಿಗೆ ಒಂದು ತರಬೇತಿ ನಡೀತಾ ಇದೆ ಅಂತ. ಸೊ ಈ ತರದ ತರಬೇತಿಗಳು ಪ್ರತಿಯೊಬ್ಬ ಶಿಕ್ಷಕರಿಗೂ ಅತ್ಯಂತ ಅವಶ್ಯಕವಾಗಿರುತ್ತೆ. ಇದು ಸಾಕಷ್ಟು ಜನಕ್ಕೆ ಗೊತ್ತಿರಲ್ಲ. ಸೊ ಹಾಗಾಗಿ ಇಂಥದ್ದನ್ನ ನಾವು ಶಿಕ್ಷಕರ ಹತ್ರ ತಗೊಂಡು ಹೋದಾಗ ಅವರಲ್ಲಿ ವೈಜ್ಞಾನಿಕ ಮನೋಭಾವ ಹಾಗೆ ಯೋಚನಾ ಶಕ್ತಿ ಬೆಳೆಯುತ್ತೆ. ಇದರಿಂದ ವಿದ್ಯಾರ್ಥಿಗಳೇ ನೇರವಾಗಿ ಯಾವ ರೀತಿಯಾಗಿ ವಿಜ್ಞಾನವನ್ನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಬೇಕು ಅನ್ನೋದು ಗೊತ್ತಾಗುತ್ತೆ. ಸೊ ಹಾಗಾಗಿ ನಾನು ಇಲ್ಲಿರುವಂತ ಎಲ್ಲರಲ್ಲಿ ಕೇಳ್ಕೊಳ್ತಾ ಇರೋದು, ದಯವಿಟ್ಟು ನೀವು ನಮ್ಮಂತ ಶಿಕ್ಷಕರನ್ನ ಆಯ್ಕೆ ಮಾಡಿ ಮೆಂಟರ್ ಮಾಡಿ, ನಮ್ಮ ಮೂಲಕ ಮುಂದಿನ ಶಿಕ್ಷಕರಿಗೆ, ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ವಿಜ್ಞಾನ ತಲುಪುತ್ತೆ, ವಿಜ್ಞಾನ ಬೆಳೆಯುತ್ತೆ. ಸಾಕಷ್ಟು ಜನ C.N.R ಆದಂತಹ ಮಕ್ಕಳು ವಿಜ್ಞಾನಿಗಳಾಗಿ ಬೆಳೆಯೋದಕ್ಕೆ ಪ್ರೋತ್ಸಾಹ ಸಿಗುತ್ತೆ ಅಂತ ಹೇಳ್ತಾ ನಿಮ್ಮೆಲ್ರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು. ವಿಶೇಷವಾಗಿ ಈ ಅವಾರ್ಡ್ ಅನ್ನ ಕೊಟ್ಟು ನನ್ನಲ್ಲಿ ಇನ್ನಷ್ಟು ಜವಾಬ್ದಾರಿಯನ್ನ ಹೊರಿಸಿರುವಂತ ನಿಮ್ಮೆಲ್ಲರಿಗೂ ಹೃದಯಪೂರ್ವಕವಾದಂತಹ ಅಭಿನಂದನೆಗಳು, ಧನ್ಯವಾದಗಳು. ಥ್ಯಾಂಕ್ ಯು.
ಧನ್ಯವಾದಗಳು ಶ್ರೀ ರಾಮಚಂದ್ರ ಭಟ್ ಅವರೇ. Thank you very much, Shri Ramachandra Bhat, for your response. Now we'll have response from Shri Annapu Punnayya. Before that, I would like to inform Shri Annapu Punnayya that the certificate will be sent to you, within a day or two. And also we are aware that, that of your desire to visit us in person. So it was not possible because of the pandemic. However, we will make sure that, we will invite you in the very near future to visit us and also to meet with Bharat Ratna Professor C.N.R. Rao and Dr. Mrs. Indumati Rao. Now we request you to give your response. Please unmute.
Yes, thank you. Thank you very much, sir. First of all, I am extremely privileged to receive this award, sir. I think every teacher in the world who has impact even on a single student deserves this award. I dedicate this award to all the great teachers on the planet who created a great students. Teaching is one of the best profession in the world. Their ultimate goal in life is proud to quality education to their students. They are ones to teach their students to differentiate between the good and bad things in life. A teacher knows that not all students are equal capable, so they put extra effort for those who are weak. A teacher good impression on his or her students impact positively, and the students considered him or her as their role of model. I am very thankful to Honorable Chairperson and Administrative Officer and Jawaharlal Nehru Center for Advanced Scientific Research and Professor C.N. Rao Education Foundation who have honored me, and I am very thankful to you and all who encourage me. And thank you one and all and everyone in this partner. Thank you very much, sir. Dhanyawad. Dhanyawad, sir.
Thank you very much, Shri Annapu Punnayya, for your response. Now I request our President, Professor G. Kulkarni, to give his remarks.
Thank you, Professor Govindaraju, Chair ETU, and Mr. Jayachandra for the coordination. Good morning. Bharat Ratna, Professor C.N.R. Rao, Dr. Mrs. Indumati Rao, Mr. Sanjay Rao, Professor K.N. Ganesh and family, Professor Krishnan, Professor Nagaraja, Professor Sood, faculty colleagues, teachers and students. I am truly glad to be with you all. We at the center, JNCASR, thank Madam and Professor Rao and the larger family, Mr. Sanjay Rao, Professor Ganesh, and other members of the C.N.R. Rao Education Foundation for making the center a part of this award program. It's an honor for the center to be associated with this activity. As we all know, the foundation has been making great efforts to promote good quality science education by way of conducting science outreach programs throughout the country, especially reaching out to rural young minds. I have taken part in many of these activities. It is good to see Mrs. and Mr. Ishwar, Chandana School, Lakshmishwar in the audience. Thank you for coming. As part of such activity, the foundation also recognizes what we are witnessing now, recognition of the dedicated science teachers at school and pre-university levels. This is a truly noble initiative. C.N.R. Foundation, in association with JNCASR, has instituted these prizes for outstanding science teachers since the year 2005. We just, a table was displayed showing the number of awardees and all. In the last 15 years, I think around 31 talented science teachers, including the present awardees, have been identified and awarded. Usually this program also goes with an outreach lecture. My colleague, Professor Sridhar Rajaram, would be giving lecture this morning. On behalf of the center, I congratulate the awardees, Shri Ramachandra Bhat and Shri Annapu Punnayya, for receiving the 2019 prizes. Hearty congratulations to you and also to your families. I wish them all the best, and as you just witnessed, the prize carries a certificate, citation, and a cash prize. I believe the cash prize has already been, dispersed. On this occasion, on behalf of the center, I would like to thank Professor Rao and Mrs. Rao for their visionary efforts towards popularization of science in India. Sir, Madam, I must tell you, this center stands and joins hands with you both in supporting such programs. Thank you all. Thank you very much.
Thank you very much, sir, for your kind remarks and also the continued support. Of course, we also take this opportunity to thank the family of Shri Ramachandra Bhat for being with us. And now, again, so it's on behalf of C.N.R. Rao Education Foundation, we would like to thank the President, Professor G. Kulkarni, for his continued support and guidance. And sir, I request you to kindly, accept a small from us, from the foundation, sir. On behalf of the C.N.R. Education Foundation, we also would like to place on record our sincere thanks to Professor V. Krishnan for being with the ETU Education Technology Unit on various activities, and especially for facilitating this selection, the entire process of selection. Thank you very much, sir. With that, we have almost come to the end of the program. I request Mr. Vinayak Pattar to give vote of thanks. Vinayak.
Good morning, everyone. We express our grateful thanks to the C.N.R. Education Foundation for entrusting the Jawaharlal Nehru Center for Advanced Scientific Research in the selection of Outstanding Science Teachers Prize Award for the year 2019. Our thanks due to the award selection committee members for helping us in the selection of the awardees for the year 2019. We express our thanks to all the outstanding science teachers, prize awardees for their kind presence. We thank all the invitees for gracing this function who are present online and offline mode. Our sincere thanks to the President of JNCASR, Professor G.U. Kulkarni, for extending his support for organizing this event. We wish to express our sincere thanks to Professor Bharat Ratna, Professor C.N.R. Rao, Dr. Mrs. Indumati Rao, and family, and all the governing council member of the C.N.R. Education Foundation. We thank the administrative officer and administration for providing the infrastructure facilities to host this event. And thank Ms. Ramya and Kalavati, Anita, Sukanya, and Praveen, Munegowda, and Peer, Dilip, and I thank all the technical team for making this event successful without any technical glitches. Okay, last but very important item on the vote of thanks. Now I request our beloved president to hand over the small gift from C.N.R. Education Foundation to Professor T. Govindraju for convening the program and directing all of us. And thank you all once again. And over to you, sir.
Thank you, Vinayak. I take this opportunity to thank Mr. Jayachandra and also Mr. Vinayak Pattar for coordinating various, coordinating the entire program. Thank you very much. Now we will break for 15 minutes, and we have refreshments outside for those in the campus, and we will assemble back here after 15 minutes for a very interesting science, popular science lecture by Professor Sridhar Rajaram. Thank you, one and all. Thank you very much.
Wait. I want to.
Hello.
Mama.
Hi.
Hi. Part of the post. Very nice. Hi.
Hi. Happy.
Hi, Sanj.
आखिर खेलते रहेंगे. Okay. Yes.
So all set. Yeah.
Okay. Okay. Sako. Hey.
No, we
Sir, namaskara. Sir, Ganesh sir, namaskara. Govindraju here. Thank you very much for joining us.
Govindraju ನಾನು ಮಾತಾಡ್ಬೇಕು ಒಂದು ನಿಮಿಷ.
Muted, I think.
Yeah, thanks, Govindraju.
Thank you very much, sir. Thank you.
Thanks for sending the information.
It's with the family.
Govindraju,
Yes, ma'am.
I wanted to say that because of this pandemic, our usual function includes a music concert and all that.
Yes, sir. Yes, ma'am. Yes, ma'am.
We forgot to mention that.
Yes, ma'am. It was my foresight. Extremely sorry. I should have mentioned that.
Anyway, in the afternoon before the lecture, you just say the entire program normally. After the lecture, after tea, there is a music program where all the invitees and school children take part. And that is actually the highlight of the program.
I'll do, madam. I'll do, madam.
Please mention this in the afternoon.
Yes, ma'am. Yes, ma'am.
Okay.
Thank
It
you.
was done
Thank you.
very nicely. You conducted it very, very well.
Thank you. Thank you, ma'am. Thank you, sir. Thank you, Sanjay.
Flawless.
Yes.
Okay.
Huh?
ಸರ್ ನಿಸರ್ಗ PU ಕಾಲೇಜ್ program.
Good afternoon. Welcome you all for this afternoon program. Again, I would like to start the program once again on behalf of JNCASR and also C.N.R. of Education Foundation. We extend again a warm greetings to our teacher awardees and their families, and also schools who are attending online, along with other more than 15 different schools all over Karnataka, and also we have schools attending from outside Karnataka as well. Before we start the program, I would like to mention to you that the awards, the two teacher awards were given, one for within Karnataka and one award for outside Karnataka. And we have the awardee from Karnataka, Shri Ramachandra Bhat ji, and then we have the teacher outside Karnataka, Shri Annapu Punnayya, who is attending along with his family and school and teachers from online an online platform from Andhra Pradesh. And also would like to mention that usually the program is a full day-long program normally, but because of the COVID-19 pandemic, the program has shortened. So it starts with the award program as we did today, this morning, and followed by a popular science lecture that we are going to have from my colleague Professor Sridhar Rajaram, and followed by a very interesting program and important part of the event is music program by an eminent musician. Usually, eminent musician will be invited to JNCASR, and we'll have the music concert of different kind. As I mentioned, because of the COVID pandemic, the music program is not been included this year. Probably we'll have that event on some other, later in the year. So with that, again, I welcome you all the students and teachers from various schools and colleges, as I mentioned earlier, from more than 15 different schools and colleges for this afternoon program that is a popular science lecture. So today's popular science lecture is going to be given by my colleague, Professor Sridhar Rajaram. So let me briefly introduce Professor Sridhar Rajaram. Professor Sridhar Rajaram is a professor, associate professor at International Center for Material Science, JNCASR, and he is also associated with CPU, Chemistry and Physics of Materials Unit, and also New Chemistry Unit. He did his master's in chemistry from Indian Institute of Science, Indian Institute of Technology, Madras, IIT Madras, and MS from Cornell University, United States. He obtained his PhD from University of Utah, again from United States, and his postdoctoral research work was from University of California, USA. And subsequently, he joined our center, JNCASR, as an assistant professor in 2009, and subsequently, he rose to the position of associate professor. His research interests are in developing organic materials suitable for low-cost electronic devices and in the field of organocatalysis. To more than that, Professor Sridhar Rajaram is an excellent teacher, and I'm sure he will, going to have, first-hand, experience of his, lecture today. He's going to talk to us, talk to you, talk to all of us on chirality, the handedness of chemical systems and life. With this brief introduction, now I request Professor Sridhar Rajaram to deliver his lecture. Sridhar, thank you.
Thank you, Govan, for the kind introduction. Let me first begin by congratulating the award winners, Mr. Ramachandra Bhat and Mr. Annapu Punnayya. It's been teachers like you that have been the reason for me choosing chemistry and science, and I hope you continue to inspire the next generation of scientists. Thank you. And I also take this opportunity to thank the C.N.R. Education Foundation that has set up this wonderful award to inspire teachers. And thank you, Professor Rao and Mrs. Indumati Rao, for organizing this. Is wonderful. Okay, so with that, I'd like to begin my lecture. I have to use mouse, is it? Okay. Yeah, okay, fine. So my lecture today is on chirality, which is the handedness of chemical systems. And it's a fairly deep impact on both day-to-day life and in biology as well. In a sense, I was first introduced to this concept at my school by an amazing teacher, and that has basically made it a point of interest for me since my time at school. Okay, so once again, it's wonderful to have this recognition for school teachers. Okay, so what is handedness? Okay, so what I would like to do in this lecture is show you that handedness is there in a lot of different aspects of our life, and this is pretty central, I would say, even to our modern day life in terms of the new materials that we make and all of that. Okay, so what is handedness? Handedness is simply what is called non-superimposability of mirror images. Okay, so this is a pretty broad definition. It doesn't require any idea of what an atom or molecule or any of that is. And this was termed chirality by Lord Kelvin. Okay, the idea here is you cannot, the mirror symmetry present in our body, okay, makes our hands non-superimposable. Okay, you can superimpose them on the front side, but the back sides can't superimpose. If you do this, the front sides don't superimpose, right? Okay, so and how is this important is something that I would like to walk you through this lecture, in this lecture. Okay, so if we take a look around, we see chirality all around. Okay, so one great example is the presence of these shells that are in opposite chirality. Okay, right? And if you go carefully look at a creeper, if you see the fresh tendrils from a creeper, you'll see that they form a nice tight spiral. And these spirals are, of course, non-superimposable. You have a left-handed helix and a right-handed helix. Of course, more commonly, if you're interested in cricket, you would have seen that you cannot put your right-handed glove on left hand and left-handed glove on the right hand, right? Of course, if a batsman is left-handed, the gloves do interchange, right? Based on which is the front hand that they play with, okay? Another great example in cricket that I would like to point out is, these two quote-unquote leg spinners. One of them is a left-arm wrist spin bowler. The other one is a right-arm wrist spin bowler. Both of them have practically the same identical action, except they deliver the ball from opposite hands, which is when they deliver the ball, they just rotate it. They rotate the wrist in this direction, okay? And you can rotate the wrist in only one direction, depending on which hand it is, okay? Right? And this imparts revolutions to the ball. And when the batsman is facing them, they may be seeing identical action, but for a right-hand batsman, Kuldeep Yadav's delivery looks like off-spin, right? He is actually delivering leg spin from his left hand. And with Chahal, it looks like leg spin. Okay? And of course, you can generate a lot of spin with your wrist than with your finger, and that's why these wrist spinners are favored to bowl even in unresponsive pitches. But the macroscopic dissymmetry that you're seeing in these things actually arise from molecular dissymmetry. And this was something that was proposed by Pasteur, okay? And he was the first person to show that you can actually have dissymmetry in molecules. And before that, okay, there was one other important discovery, which is about polarization of light, okay? So light is basically a combination, it's an electromagnetic wave, and it has an electric vector and a magnetic vector, which oscillate in all directions. But when you put it through a polarizer, you get oscillations in one direction. And it turns out if you have a second polarizer exactly crossed to this, if it's aligned in the same direction, it will let it pass through. But if it's 90 degrees perpendicular, it stops the light from going out. Okay, and the first person to observe this was a French scientist named Jean-Baptiste Biot. And what he showed, more importantly than just showing that you can use two cross polarizers to stop light, is what he showed is there are certain molecules that you can put in between these two cross polarizers. And now if you want to stop the light from coming out, you have to actually rotate the polarizer. So it's no longer just perpendicular, you have to rotate it to some other angle. So why is this happening? And the obvious answer that he was able to figure out is that the whatever substance you are putting in between the two polarizers is itself rotating the plane of polarization. Therefore, you have to cross the polarizers in a different angle to completely stop light from going through. Okay, so what he found out was there are a lot of natural substances that were doing this. Okay, not all of them, but some of them. Okay, and it was quite a bit of a mystery about why this was happening, but people slowly started observing this with a lot of different organic molecules. And this is where Louis Pasteur, okay, of course, everybody knows Pasteur, and one of his first experiments as a scientist was trying to, one of his first projects rather, was trying to figure out what was causing this difference in plane of polarization, okay? So at that time, when he was a researcher, it was very well known that there are two kinds of tartaric acid. One is a dextrorotatory tartaric acid. That is, if I have a solution of tartaric acid and put it between two polarizers, the dextrorotatory tartaric acid rotates the plane of polarization to the right, and there is an optically inactive form of tartaric acid. Okay, so at this point, scientists were able to clearly understand what the chemical composition of tartaric acids were, and they knew that these were, in terms of molecular formula, the exact same compounds. So it was a big mystery why one of them was rotating plane polarized light while the other one was not. Okay, and this is the problem that Pasteur was able to solve. Okay, what he was able to show was that if you take a sodium ammonium salt of this tartaric acid, it crystallized into two different crystals, which are exact mirror images of each other. Okay, now I've shown pictures of the crystal here to give you a perspective about how difficult it is to differentiate these two. And these are, to give you a better idea, these are micron-sized crystals. Okay, barely some of them are millimeter-sized crystals. Okay, so Louis Pasteur was able to look through a microscope and pick out crystals of one habit different from the other habit. Like it's like picking out a bunch of right-handed gloves and left-handed gloves from a large bin of gloves. Okay, he was able to do this painstakingly and showed that when he dissolves each of these crystals in solvent, they rotated plane polarized light in opposite direction. Okay, so this was kind of a big breakthrough at that time, and the big scientist at that time was Jean-Baptiste Bayot. Okay, and he didn't believe Pasteur. Okay, he said, "Okay, this is too fantastic. You have to come and show me that this really works." So Pasteur traveled all the way to Paris. Okay, and he did this experiment in front of Bayot and showed that it does, rotate light in different directions. And this is a fairly important aspect of science in general. Okay, so it is not just important to claim that you have made some great discovery. It is important to actually show in front of other people that you have what you say you do. Okay, and in the 19th century, it used to be done in front of a large audience doing experiments and all of that. These days, we do it in terms of sending out papers for publication where your peer group evaluates it. Okay. So one key thing was with Pasteur, he did not understand the molecular reason behind optical activity. He knew that, okay, there are two kinds of tartaric acid. One rotates with one direction, the other in the other direction, but why were they rotating? But he was able to make a guess that it's got to be something to do with dissymmetry at the molecular level. Okay. So another big breakthrough in terms of how this is not just something that is a curiosity in terms of chemicals. Okay, so what he wanted to show was this is actually important in biological systems as well. Okay, so what he did was he was able to show that if you take a mixture of two tartaric acids, microorganisms can selectively ferment the plus tartaric acid in paratartaric acid. Okay, microorganism is able to differentiate one kind of tartaric acid from another one. Okay, and this leaves behind pure minus tartaric acid. Okay, so in a sense, this was the first example that showed that biochemical processes, biological processes, relied on chirality. Okay, and once again, I want to emphasize that the person who actually showed why this is happening is not Pasteur, but another scientist. But before we go into that, so I want to talk about a general problem that chemists were puzzled by in the 1870s. Okay, and that was the problem of dichloromethane. Okay, so dichloromethane is essentially one carbon that has two hydrogens attached to it and two chlorines attached to it. Now, if I were to think of arranging that in a what is called a square planar form, I can see that I have to get two different isomers, one in which the chlorides are close to each other, one in which the chlorines are far away from each other. Okay, right? So these two arrangements are possible. Okay, but try as they may, the chemists were not able to, separate, quote unquote, separate these two isomers. They had to conclude that there was only one isomer possible. Okay, so why was this the case? Okay, this could be understood if you go and take planarity out of the picture. Okay, so if you understand this in terms of dichloromethane being a tetrahedral structure, okay, so I have here a model of a tetrahedral carbon with two different attached with two substituents. Okay, right. So you can see that it is no longer planar. So let me make a quick demonstration here. Okay, so I put my first chlorine on here. Now I can put my chlorine anywhere among these three, right? So I can put my second substituent anywhere on these three and I'll get the same molecule, right? So unlike having a square planar structure, if you go to a three-dimensional structure, you're able to see that it can have only one isomer. Okay, so what Van 't Hoff and Lebel were able to clearly demonstrate was not just explain, not just this idea of going three-dimensional, not only explain the lack of cis and trans isomer, but it also helped in explaining optical activity. And Van 't Hoff was clearly able to do this by making cardboard models of tetrahedra, okay? And these are the original models that he made, and there's a picture I got from the web. And I guess they are still exhibited somewhere in one of the chemical museums, actually. So pretty interesting. All he did was, make tetrahedra from cardboard and explain one of the biggest problems in science at that time, okay? The molecular nature of chirality was understood, but the idea of that impacting biological processes was still a mystery. And one of the big discoveries in this was a discovery of a new form of an amino acid called plus asparagine. Okay, this is one of the 20 natural amino acids that are seen in proteins, enzymes, and all of that. What this scientist Arnold Opaiuti was able to discover was a new form of asparagine that was dextrorotatory. Okay, and he had a very unusual test for differentiating the plus and minus forms. Okay, of course you could put them between polarizers. Okay, see which way they rotate the plane of polarized light. Okay, but this is not a test that I would recommend anyone else do, and this is basically a test of taste. Okay, it turns out the plus form is completely sweet, while the minus form is has no taste. Okay, very interesting. What we see is why does this happen? Okay, and this happens because we are tasting it through receptors in our tongue, and these receptors in turn are made from proteins, essentially. There are proteins in our tongue that recognize the plus form and minus form differently. Okay, these proteins, where do they get their chirality from? As we all know, proteins are chains of amino acids, and each of these amino acids in turn is chiral. Okay, except for glycine. Okay, so you have a chain of chiral amino acids, and because of the chirality of the center, there is three-dimensional chirality, and they're able to distinguish between minus asparagine and plus asparagine. Okay, so how does this work? Let me just quickly give you an idea of, okay, before we go into that, this kind of difference in isomers was also observed by Emil Fischer, where he showed that this structure, which is a glucose derivative, can be hydrolyzed by emulsion of bitter almonds, but this opposite isomer, you can see that these are the two different isomers, is hydrolyzed by maltase from yeast. Again, the biological processes that are responsible for doing this chemical reaction are dependent on proteins, okay, and proteins themselves are chiral. Okay, so what is exactly happening here is proteins being made of amino acids, which are chiral, are able to selectively bind. Okay, so how does this happen? So before we go into that, I want to show you something about chirality. Okay, so I have a model here, okay, of a tetra-substituted carbon atom. You can see here that these molecules are mirror images of each other, right? Okay, so now if I try to superimpose them, what do you see? I can superimpose the red ball and maybe the back side, but the white and blue don't superimpose, right? I can do the same thing trying to superimpose the blue and the black part, but you see that the red and white don't superimpose. Okay, I can get any two to superimpose, but the other two will not be able to meet each other. Okay, and this is exactly the interaction that is happening in enzymes. Okay, so let us imagine I put in a restriction saying, so my hand is also chiral, right? So let's just say let's put a restriction saying, the white ball has to be on my index finger, okay? The red has to be on my little finger, and blue has to be on my thumb, right? Okay, so now you can see that I can do this with one of the molecules, But if I do it with the other, these two get interchanged, right? Of course, I can do the same thing with my right hand. Now I get an exact fit, right? This is essentially how enzymes are able to recognize one molecule. So you can imagine my hand being like a enzyme binding pocket. It's able to clearly distinguish the two isomers. Okay, that's what I've shown here. In A and B, I have a interaction between D and X here, which is very strong interaction. Now, once I switch the configuration, that is by changing D and A, that interaction is broken. So enzyme is no longer able to bind this. And the similar thing is shown here in terms of having two chiral centers. So in the first structure, you can see E prime and E are able to interact. D and D prime are able to interact. C and C prime interact. D and B prime interact. Now, if I just change one chiral center, that is by switching A and B, I lost my B prime interaction here, right? So enzyme is not able to recognize this anymore. And that is the underlying basis for why we are able to, get a sweet taste for one form of asparagine and the other form being tasteless. Okay. So now we scientists have grown to recognize that this is a extremely important thing, especially in the field of medicinal chemistry. Okay, what I'd like to show you is two kinds of standard treatment for Parkinson's disease. Okay, to this day, the standard treatment option is having L-DOPA or minus DOPA and plus DOPA. Okay, so this is used to treat Parkinson's disease. This is actually pretty toxic. So you can imagine if you're giving DOPA as a medicine to someone with Parkinson's, you need to make sure you're giving only minus DOPA, okay, and not plus DOPA. Okay, the same thing goes for penicillamine, which is used for treating chronic arthritis. Okay, whereas the R-penicillamine is highly toxic. Okay. So the solid triangle means the NH2 is coming out of the plane. The dashed triangle means it is going behind the plane. Okay, right. So this kind of chirality we now understand is coming from a carbon having 4 different centers, just like 4 different substituents. Okay, so it is interesting that chirality can be exhibited not only in carbon but also in phosphorus. Okay, so this is something a lot of us have become unfortunately familiar with, remdesivir. One of the challenges of making remdesivir is getting this phosphorus in a single configuration, getting the correct configuration around this phosphorus. This is a significant challenge, and it's one of the reasons why it is difficult to make remdesivir on a large scale. Okay, so there are other interesting aspects to this, and I want to tell you one story about a disease called thalassemia. Okay, I want to talk about siderophores, thalassemia, and chirality. Okay, so let's just take a kind of a detour. Okay, so one of the important nutrients for bacterial growth is iron. Okay, so bacteria cannot grow without this. Okay, of course, we also need it for our hemoglobin. Okay, now how do bacteria take this up from environment? Okay, there is a chemical problem because the most common oxidation state of iron in the environment is +3, and it is present as a hydroxide, and it has very poor solubility. Okay, right. So if it has very poor solubility, how do bacteria take it up? Okay, it's not like they can just pick up a bunch of iron and put it in their mouth. They have cell membranes, and this iron has to cross the cell membrane, right? The way the bacteria are able to do this is by releasing compounds called siderophores. Okay, what are these siderophores? Okay, these siderophores are nice chiral molecules that are released by bacteria. They go and complex the iron. Now you get a soluble form of the iron, and now that complex has what is called a receptor on top of the cell membrane. That is basically a gate. That gate happens to be chiral. Okay, and just lets the siderophore complex with the iron back into the cell. The bacteria breaks up the siderophore and then takes up the iron. Okay, now these are some of the most the best or the tightest binders of iron out there. Okay. Now, why is this important? Okay. Let's take one other detour. There is a blood disorder called thalassemia. There are a lot of people who suffer from this, and in fact, this drug actually, the drug used for iron accumulation, I'll come to that in a minute, was in short supply during our pandemic. Okay, so this is a blood disorder where hemoglobin is not present in sufficient amount, and patients have to undergo regular blood transfusion. Okay, and if they take up regular blood transfusion, this results in iron accumulation in the body. Okay, right. We all think that iron accumulation is great, we become more powerful, but it comes with its own set of problems. Okay, iron accumulation can lead to growth of unwanted bacteria. Okay, nice and interesting fact is in our stomach. Okay, we have more bacterial cells than human cells in our entire body. Okay, so we have more bacteria than humans, but these bacterial colonies are very, very important for maintaining good gut health. And it turns out they're also important in a lot of neurodegenerative disorders as well. Okay, so the moment you disturb this balance, the moment you have the wrong kind of bacteria growing in your stomach, you end up in serious trouble. Okay, so whenever there is an iron-rich environment, all kinds of bacteria start to grow. So thalassemia patients have a problem. Okay, they receive regular blood transfusion, and they have to, take up something to remove their excess iron. Okay, right. Now, what do? We know how to remove excess iron from the environment, right? We can use siderophores, right? So the answer seems to be simple. Okay, treat the patients with siderophores. Siderophores will complex the iron and aid in excretion, right? That's a brilliant idea, but only partly, because if you put in siderophores, bacteria can also use the siderophores to take up iron. Okay, right. So what's the solution? Well, recall that the bacteria release siderophores out into the environment. It takes up iron, but when it comes back, there is a chiral gate through which the siderophore has to pass. Okay, and the clever idea here is the siderophore that is used is itself chiral. Okay, there are two chiral centers here. Right, so I take a L-fluoabactin and give it to a patient. Okay, they'll of course complex the iron and excrete it, but I don't suppress bacterial growth because this can be taken by bacteria as well. Okay, and this D-fluoabactin, okay, will go complex iron in the same manner. Remember that optical isomers have identical energy content, right? So their interaction with chemical entities that are not optical active or not optically active will be identical. So the way this L-fluoabactin and D-fluoabactin interacts with iron is going to be identical. But once it forms the complex, this cannot pass through the chiral gate that bacteria have for letting the siderophores through. Okay, so now if I give this as the chelator for removing iron, okay, I can safely excrete out iron from thalassemia patients. Okay, this actually turned out to be a problem during COVID because thalassemia patients weren't able to get these drugs very regularly. Okay, now we've already seen this. So what are the big questions in terms of what are the things that really interest researchers in this area? Right, so we've seen that there is practically, in medicinal chemistry especially, there are some unanswered problems. So first question, okay, so if minus dopa is good for treating Parkinson's and plus dopa is toxic, okay, I have to be able to give patients only minus dopa, which means I have to be able to make minus dopa selectively. Okay, how do I make chiral molecules selectively? Okay, is life possible without chirality? Okay, how did chirality originate in our planet? Okay, so these are some of the big questions that researchers try to answer, and I can tell you right away that we've made good progress as scientists in answering the first question. Okay, the second question is the answer to that is probably no, but we don't have a definitive answer. And the third question we have no ideas. Maybe the next generation of scientists in schools, maybe one of you will be able to solve this. Okay. So one of the first reactions that was shown to be selective in giving a single enantiomer was in the synthesis of DOPA. Okay, so that's why I was referring to DOPA over and over again. So William Knowles discovered this process where he could do a hydrogenation of this substrate and get a chiral molecule. Okay. And another stunning discovery was made by Professor Ryoji Niori. And we've all been, and I've also been talking about how molecular symmetry, or rather macro dissymmetry, comes from molecular symmetry. And I told you that it comes from chiral carbons, right? Meaning carbons that have 4 different substituents. What Niori was able to show is that you don't need a chiral carbon to get chirality. Okay, so what he showed was these kind of molecules that have only planar carbons can still exhibit chirality, and he was able to show that these are very useful as catalysts in making chiral molecules. Okay. A third, so this person shared the Nobel Prize with William Knowles. Okay, of course. Let's come to our remdesivir. Okay, so one of the key problems here is there are many methods now that have been developed by chemists for making chiral carbons. Okay, and there are very few methods for making chiral phosphorus. Okay, and this is in fact one of the big challenges in terms of making remdesivir. Okay, and that's why it was expensive. That's why there are shortages. Okay, of course, the efficacy of this for treating COVID is also, not clear cut, but one of the important aspects of making this is making the phosphorus centered chiral. Okay, and that turned out to be a difficult one. Yeah? So this is kind of interesting in the sense people have started now with the rise of nanotechnology and nanoscience and all of that. People have started to look at what would a motor look at on an atomic scale. Okay, so it turns out, molecules, although we draw them as static pictures of tumbling around, moving around, stretching, rotating, and all of that. Okay, so they're naturally rotating. But the challenge Professor Ben Ferringer wanted to answer is somehow, can I make them rotate in only one particular direction instead of rotating in all different directions? Okay, so he has called these molecular motors. And what he has shown is if you take chiral molecules, okay, so I don't want to spend too much time in this because it's a little difficult to visualize this. So it turns out if you introduce chirality in the molecule, you can get molecules to rotate in different or in a single direction. So these are called unidirectional molecular motors. Okay, so we've talked about chirality in medicinal chemistry and biological systems. There's another aspect of life where stereochemistry plays a really important role. Okay, and that is in in terms of the plastics that we use. Now, we all know right now plastics are a dirty word, okay, but modern life is just not possible without plastics, okay, and I would argue that it's not plastics that are the problem, but it's the way we use them. It's the way, or rather the way we abuse them, that's the problem, okay, right. One of the most common plastics that we all use is called polypropylene, okay, so you take propylene, use a catalyst, and you get a polymer. Basically, you add propylene molecules like growing a chain, and you get polypropylene. Okay. Now this is a big discovery. It was a discovery that won a Nobel Prize, and it's called the space age plastic. Okay. Right. There's an interesting aspect to this polypropylene. Okay. So now I've showed you that this is like a chain of carbon atoms, and on every third carbon atom, there is on every second carbon atom, there is a methyl group. Okay. Now, if all of the methyl groups point in the same direction, we get something called an isotactic polystyrene. Okay. This water bottle cap, okay, are made of isotactic polystyrene. Okay. You can see it's pretty hard. Okay. I also have here a sample of polypropylene where the methyl groups are randomly oriented. Okay. You can see how this is a nice stretchable, foldable, crushable polymer, just like, you're chewing gum. Okay, right. So depending on how I arrange these molecules, okay, the methyl groups in this molecule, I get either a hard plastic or a tacky material. Okay, so I'm pretty sure all of you have come here in some vehicle or the other, and the vehicle has a lot of plastic components. Okay, right, your front fender and all of that. Okay, if you do happen to hit another vehicle, you hope it isn't made of plastic like this, right? Okay, you hope it is made of materials like this. Okay, so you can see that it is actually pretty important. Okay, so now the big question, okay, how did chirality originate on Earth? Okay, so this is something that we don't have a very good answer for. Okay, but what is certain is if I have a small amount of chirality, I'll be able to amplify that into a large amount of chirality. Okay, and a wonderful reaction is shown here where this particular compound with a low enantiomeric enrichment, when it is treated with zinc, forms a complex. Okay, this complex is able to resynthesize this molecule in an enantioselective manner. Right. So what I get is take a small amount of difference in the enantiomer content and amplify that into a large difference. Okay, and we really think that this is how chirality must have originated in Earth. Some small differences in chirality, local differences, must have been amplified into the large chirality that we see in our daily life today. Now, what is the exact molecular mechanism? What are the reactions that led to this amplification? Is something that we are not yet clear, and maybe one of you will discover this. Okay, and with that, I come to the end of the talk, and I'd be happy to answer any questions.
Thank you very much, Sridhar, for that wonderful talk. Now the talk is open to questions. Probably we can have few questions from online. Okay.
Is the question about origin of chirality, or is it about the breaking of chiral symmetry? I mean, the population of the left-handed and the right-handed molecules not being equal. Is that the question, or is the question about origin of chirality itself?
It's okay. So, okay, what I meant by origin of chirality is how did the symmetry break happen?
Yeah, that's right. Yeah,
okay.
That's right.
So, because what happens is all of these chiral molecules are essentially made from flat molecules.
Yeah, yeah.
Okay, so when you have a flat molecule that goes to a three-dimensional molecule, it will go to both types in equal probability.
Yeah, yeah.
Okay, somehow you have to ensure that the flat molecule goes to a three-dimensional molecule in only one way.
Yeah, I understand.
Okay, so we are able to do that in the lab.
Yeah, yeah.
Okay, but how did it happen at first? Okay, so that's the question.
So the symmetry breaking and then the amplification is what you're talking about, and
yes,
that could be one of the reasons for this. Okay.
Yes.
Yeah. Thanks.
Any other questions from online WebEx platform? Please, if you have a question, please unmute yourself and ask. Okay. You have a question? Yeah, please go ahead. There is a microphone.
Not the problem, but the way which we are using,
Yes.
where we went wrong, because actually we have a notion that plastic is what to say, it is dangerous to the environment. Please elaborate on it.
So there are several layers to this question. Okay, one is when we litter, when we abuse. okay, when we don't recycle. Okay, so one thing we should definitely do is reduce our consumption, reduce, reuse, and recycle. Okay, so now the second part of the problem is in recycling. Okay, the problem is we use different kinds of plastics. Okay, right? So we use polypropylene. This is made of polycarbonates, and I can probably, yeah, this is made of nylon. Okay? So we gather all of the plastics into one plastics bin. We try to recycle it physically by melting it and making new objects out of it. Now it will look like a nice uniform mixture to the naked eye when you do that. Okay, but if you look at it under a microscope, these are all small domains of different plastics that are distributed like a mosaic floor. Okay, so now that becomes really weak. Okay, so those kind of materials are not very strong, and because of that we enter into recycling problems. Okay, so definitely there is a portion of it which is just abuse, littering. You have a cup of coffee and just throw out the plastic wherever you are. There's a portion of it where there is genuine recycling problem, and this is something that scientists are trying to address. So come up with new plastics that can be easily recycled, okay, and come up with some kind of plastic that can be used for multiple purposes, not just one application, one plastic. That's not a very good solution, right? Because recycling becomes a problem. See, practically from a standpoint of an end user, if you tell me that, okay, segregate paper from plastic or dry waste from wet waste, I'll do it. If you tell me, okay, segregate polypropylene from polycarbonate, that's not going to happen. Okay, so there is a chemistry problem. There is a science problem to this. Okay, and there is, of course, an abuse problem in that we can easily reduce. And I mean, we have stopped using plastic bags to a large extent, right? So that's a good thing. So I think we can, by a combination of several approaches, we'll be able to actually solve this problem. Yes, we created it, we'll solve it. Yeah.
Thank you, sir.
Yeah.
Enzymes are discovered to break down these.
Can you please? Yeah. Okay. Yeah, please.
Yes.
Any enzymes are discovered to break down these plastics?
Yes. So again, there are different kinds of plastics. So some of them are polyesters, right? They are like the yarn that is used in our clothing. They're inherently biodegradable because there are enzymes that cut down or break down esters, and they're present everywhere in soil bacteria and all of that. Okay. In fact, let me give you one example. There is a polymer called polylactide. Okay. One of the great applications of this is in self-dissolving stitches. So imagine someone has a surgery in their liver. Okay. You cut open that stomach, you do surgery in the liver, right? Stitch up the liver, then stitch up the stomach. Okay? Of course, after a few days, the stitches on the stomach are removed. No one's going back in to remove stitches in the liver. Okay, that's just not possible. So what happens? So this polylactide is a nice, interesting polymer, which will slowly dissolve out because there are enzymes in our human body that will degrade the polymer over a period of time. Okay, so that's one example. And then there are these what are called drug-eluting stents that are placed in certain parts of our body. The enzymes slowly degrade those polymers and release drugs in a slow manner. Okay, so that's another application. So yes, even the polycarbonate that I talked about, okay, they are also actually biodegradable. Okay, the problem is when they do biodegrade, they generate a toxic material. Okay, so a large number of scientists are trying to address these problems, and hopefully we'll have some good solutions in the next 10-15 years. Yes. So the short answer is yes, there are enzymes that do degrade polymers, depending on the kind of polymer.
Is it possible to mix them during the preparation of these plastics?
So that they have a so the interesting thing is, okay, that could be possible. The problem would be that these plastics are actually processed at very high temperature. So let me give you a simple example. Let's say I have a plastic cup for drinking tea. Okay, now that plastic has to be able to withstand the hot tea, right? Which means if I have to make the cup, I have to make it at an even higher temperature, right? And enzymes typically don't survive at that temperature, right? So it is best to have a polymer made from monomers that can be degraded easily by enzymes and soil bacteria, or we can collect them separately and put them in a generator and bioreactor and get them to degrade selectively. That would be the best way forward. And there are companies that are doing this, even with something like polystyrene, the styrofoam, which is a pretty difficult molecule to degrade enzymatically, but there are researchers and companies working on how to address that. They're able to recycle most. So chemical recycling is the solution. Okay, physical recycling is a problem because plastics don't mix well, and that generally weakens plastics. Chemical recycling, where you break down the polymer back to its monomers, is the best way to go, and there are enzymes that do that. Yes.
Unmute, because the online people can hear.
Why
Excuse me, sir.
Yes.
I have a question.
Yes.
Sir, can we comment that chirality originated with the evolution of human life?
No, could you please repeat the question? I wasn't able to hear it properly.
Sir, can we comment like chirality originated with the evolution of human life?
Definitely not with the evolution of human life, because humans are, apparently the last word in evolution. Okay, but life has been going on much before humans. Okay, so definitely, it looks like, okay. So the way to think about this is, life depends a lot on selectively taking up materials, selective interactions, and all of that. Okay, so. So for example, if I'm able to selectively bind something in the environment, right, and not bind whatever impurity is there with that, okay, so that makes it possible to have life. Okay, that kind of selectivity is possible only with chirality. Okay, not that easy without chirality. So if I had to take a guess, I would say that life would be impossible without chirality. Okay, so many selective interactions are needed, recognition and all of that. That chirality would be built into any life system. Okay. Yes. So your question.
Please go ahead.
So that's what, plastic polymers. Why we don't have any chemical method to disintegrate or degenerate?
We do have chemical methods to disintegrate and degrade the polymers. The problem is what kind of polymers we make. So all polymers are made by stitching together small molecules. Now, what precisely are the bonds that are used to stitch these monomer units together defines how easy it is to break them. Okay, so from a chemistry perspective, if it's a carbon-oxygen bond, these are a little bit more reactive, okay, and more easy to form as well as more easy to break. But unfortunately, some of the polymers like styrofoam, polypropylene are made by connecting carbon-carbon bonds. These are somewhat harder to make and very hard to break down. So the dissolving polymers that I talked about is all made with carbon-oxygen bonds. So that we can break down fairly easily. So we have to migrate. So we have to be able to make these kind of degradable polymers that meet our mechanical requirements. So some of them do, some of them don't. Okay, and it is used everywhere. Okay, it is not just in water bottles. It is used everywhere. It's used in spacecraft. It's used in our automobiles. Okay, so there is an amazing amount of application. It's used in biomedical devices. So we need polymers that can actually be applicable, range of mechanical properties, which has carbon-oxygen bonds instead of carbon-carbon bonds. And that's, in a nutshell, is the chemistry problem behind this.
Sir, cell membranes are said to be selectively permeable. Whether in the cell membrane is any kind of gates, chiral gates are there?
So cell membrane, there are two permeability issues with cell membrane. One is a cell membrane has what is called hydrophobic or water repelling part, and it is hydrophilic or water attracting part. So the water repelling part come together, and the water attracting parts are on the outside. So that's your cell membrane. Cell membranes can selectively get molecules through depending on their ability to partition between oil and water. Okay? That's one basic level of selectivity. The second level of selectivity is, what's the whole point of having a cell membrane if you're going to let everything through, right? So, but at the same time, we have to take in nutrients, we have to take in, from the environment, right? So if that is going to happen, how are we going to make sure that we are able to have this barrier, but at the same time selectively let things through? So it turns out the cell membrane is not plain, but it is decorated with a lot of proteins. These proteins act as gatekeepers, right? And they'll selectively let some things through the membrane and keep others out, okay? And these proteins, in turn, being made from chiral amino acids, exhibit chirality, okay? If it is a simple ion like chloride or sodium, of course, there's no chirality involved. But if you have to take up sugars, okay, and it has to pass through this barrier, and the way it passes through is like there are multiple mechanisms, but especially in the brain, there are special receptors for taking up glucose. Okay? So brain has a special kind of membrane called blood-brain barrier, which won't let anything through. Okay? So there we have receptors that will effectively bind to the nutrient, pull them into the cell. Okay? So as I said, pretty complex in terms of the number of receptors we have for different things on our cell membrane.
Okay, maybe we'll take one or two questions from online quickly.
Sir, I have a
Excuse
question.
me, sir.
Yes.
Sir, I have a question.
Yeah, please go ahead.
So the proteinaceous polypeptide bonds present in our body, sir, is it a
Yes.
concept of chirality?
So the proteins are made from amino acids, and the peptide bond itself is not, three-dimensional. But there is usually, if I can you go back to the slides? The peptide bonds themselves are not where the chirality comes from. The chirality comes from the side chain.
Answer.
So you can see
Hello,
that.
sir. I have.
Yeah, one second. Let me finish answering this question. So you can see that this is actually a chiral center. Okay, and because of the protein being formed with a large number of chiral centers, the protein itself becomes three-dimensionally chiral. Okay.
Yes, sir. Thank you.
Go to the next question.
Hello, sir.
Yeah, please go
Yes,
ahead.
please go ahead.
Sir, I am not getting the point that Pasteur said that microscopic dissimilarity arise from molecular dissimilarity.
Okay, so he is basically trying to understand how a microorganism is able to differentiate between two molecules. So if you look at the size of a molecule compared to the size of a microorganism, the size of a molecule is very small compared to a microorganism. So how is it able to selectively take up one, degrade it, and
The answer.
the other one out?
Excuse me, sir.
Yes.
Sir, why is chirality so important in biochemistry?
Why?
Okay.
One second. So let me just finish answering the
Please
previous question.
hold on. So, yeah.
So what Pasteur suggested was, since these are molecules that are rotating plane of polarized light in opposite direction, there must be something in the structure that makes them rotated. And if there is something in that structure, then a microorganism is able to basically distinguish them based on the structural difference. Okay, so that's what Pasteur was saying when he said the macroscopic difference is dependent on molecular dissimilarity.
After finishing, they told they will ask.
Yeah, please ask your question.
Sir, I am sir from School Channel Lakshmeshwar, sir, District Gadag, sir.
Yeah, please go ahead. Very good.
Sir, why is chirality so important in biochemistry, sir?
So all biological processes are mediated by chiral molecules, whether it is DNA, RNA, protein, sugars, So, there is, so there is no life without chirality, okay? So in a sense, all of the, so if you think of human beings as a bag of chemicals, we are a bag of chiral chemicals, okay? So without chirality, there will be no biochemical processes possible, yeah?
Sir, a small
sir.
doubt.
Thank you, sir.
Yeah.
Sir,
Please.
is there any chiral alternative to siderovirus in treatment of thalassemia?
I don't understand the question. Can you?
In
please repeat?
thalassemia, use in your lecture said that we use the siderovirus, especially D-fluviabactina.
So, So generally, so the thalassemia patients are advised to take iron chelators. Okay. And if you are taking an iron chelator, of course, you are going to facilitate dissolution of iron, which is favorable for throwing out the iron as well as for uptake by bacteria. So there has to be some kind of chirality involved in making sure that iron is excreted but not taken up by bacteria. So it is pretty critical having chirality. Okay.
Yes, sir. Thank you, sir.
Excuse me, sir, I have one question. I am Prashant from Purchandan Lakshmishwar Gadak from 10 Chandan. Sir, how is chirality used in modern day medical chemistry, sir?
So most of our drugs, so if you look at drugs from earlier, let's say from 1950s and the drugs from 1990s and 2000, you'll see that most of the newer drugs have chiral centers in it. Okay. And these drugs are more selective, they reach their target more effectively and target only the defective parts without touching the so for example, if you have a cancer treatment drug, it has to go selectively into cancer cells and not into normal cells, right? So that requires some kind of selectivity, okay? So like that, in a lot of diseases, you want to selectively target one protein, one receptor, or a particular sequence of DNA. So your selectivity factor improves when you use chiral material, yeah?
So thank you. I think we'll stop here. We have kind of come to the end of the program, and the planet Earth is dominated by chirality, and looks like asymmetry is the way of life, not just for humans, but for the entire life. It's just that we don't probably kind of realize or given enough importance. And I would like to thank Professor Sridhar, Rajaram for taking all of us through this very, very interesting topic, chirality. And in fact, he covered almost every aspect, where, the chirality plays a important role in such a lucid and very, very, kind of a descriptive talk, lecture. And I'm sure you all agree with with me that, we all enjoyed this talk. And on behalf of the JNCASR, C.N.R. Rao Education Foundation, and also on behalf of C.N.R. Rao Hall of Science and Education Technology Unit, I would like to thank Sridhar for this wonderful talk. And then I have a pleasant duty. Sridhar, please. Yeah, on behalf of C.N.R. Rao Education Foundation and JNCASR. So, so now I request Mr. Vinayak Pattar to give a vote of thanks. Vinayak.
Thank you very much, sir. Now it's time for vote of thanks. On behalf of C.N.R. Hall of Science and Education Technology Unit, we express our thanks to Professor Sridhar Rajaram for giving us wonderful and interesting lecture. We thank the President of JNCASR, Professor G.U. Kulkarni, for extending his support and facilities for this program. Our sincere thanks to Professor T. Govindraju for convening the award and lecture program. We thank Mr. Dwarkanath for coordinating with the schools and colleges in Bangalore to participate in today's program. We thank the principal and students and teachers for participating in today's event from various institutions, from the online and the offline mode. Okay, we thank all the resource persons, the supporting staff, and the administration for the providing the infrastructure, facilities, and administrative support for this program. And I thank awardees, both the awardees. Thank you, sir. Last but least, and I'm very thankful to the technical team, Munegowda and Srinivas, Peer, Praveen, Dilip, and whole team. Thank you, one and all.
So, thank you again. So thank you very much being part of this very event, and goodbye. Thank you. All the coordination said.